Good morning, class. Today we are going to discuss about determinants, the definition of determinants, and some computational properties. First definition, the determinant of a matrix A is denoted as DET, right? We usually call this det of A. Sometimes people also write A in the pair of signs that look like the absolute value sign. But I would like to emphasize that this is not the absolute value sign. For 2 by 2 matrices, so this is the matrix, 2 by 2 matrix, and the determinant, right? Now, one more thing I need to emphasize it, you write like this, then it's not determinant anymore, it's the matrix. So be careful of what you write. Right. For 2 by 2 matrices, its determinant is equal to the product of the entries on the main diagonal subtracted by the product of the entries on the minor diagonal. For matrices of bigger size, then we are going to compute in the following way. Suppose you have a matrix of size n by n rows, n columns, and n is more than 2. Then we can compute by the expansion formula. You can expand it along the first row. Now, when you move along the first row left to right, you are going to see the first entry. Take it out, and then you multiply with the determinant of the matrix that is obtained from the big matrix by deleting the row and the column that contain the entries that you just taken out. So in this case, because you took out A11, then you need to delete the row and the column that contains it. What's left is this matrix. This is a matrix of smaller size, right? Because you deleted one row and one column, so its size is going to be n minus 1 times n minus 1. And this is A11. This guy. Then you move to the next one. Now here comes the problem about the sign. Right? For expansion, the first one on the first row is corresponding to a plus sign. So you actually have a plus here, but because the plus doesn't change or make anything change, so that is why we ignore it. But the next one has to be the minus. If you have the next one, it's going to be a plus, and if you have the next one, it's going to be a minus, and then plus, and then minus, and then you keep moving until the last one. Now, anyway, we focus on our second one here, A12. All right, so we pick it out, put it here, and the sign in front of it is going to be negative, is a negative sign. You multiply this with the determinant of the matrix obtained from the big matrix by deleting the row and the column that contain the entry that you just taken out. So that means you will have to delete this guy and this guy. Now what's left is going to be this smaller matrix. Of course, that is of size n minus 1 by n minus 1. All right. And you keep doing so until the last entry on the first row. All right, so then the last one you will encounter is the last entry. Right? You delete the row and the column that contains it. Now, because we don't know how many columns we have here, so we can by no way identify whether we have a plus or a minus, right? If we have an even number of columns, then it's gonna be a minus, right? 1, 2, 1, 2, right? If the number of columns is even, that's gonna be a minus. If the number of columns is odd, then that's gonna be a plus. So the way to write this down is that we utilize the notation that we are familiar with from the alternating series from calculus 2. So we write -1 and then to the power n plus 1. Let's double check. If the number of columns were odd, then odd plus 1 meaning even, so you're going to have a plus. If the number of columns is even, then even plus 1 is going to be odd, and that's going to generate a minus. Now in practice, you wouldn't have to worry about this part because the plus and the minus will be generated very naturally. Just 1 plus, 1 minus, 1 plus, 1 minus. That's it. Let's compute the determinant here, right? 2 by 2 determinant, 3 by 3, and 4 by 4. Just using the definition here. This and this. Alright, so for the first one, it's a determinant of a 2 by 2 matrix. So you multiply along the main diagonal, so 2 times -5, and then minus 4 times -3. So this is going to be -10 minus -12, and that's going to be 2. Now for the second one, it's a 3 by 3 determinant. Or in other words, the determinant of a 3 by 3 matrix. So we have to expand along the first row. You are going to have plus, minus, plus. So you can see that in practice, the plus and the minus will be determined very easily for the last column. So this is a plus, so I wouldn't have to worry about it. I can just ignore it, right? The first number is 1, so I write 1. Then I'm going to delete the row and the column that contains the number 1. So you delete this and this. You are going to get 5, 8, 6, 9 left. So you multiply 1 with 5, 8, 6, 9. Next, you are going to subtract 2 times the determinant obtained by deleting the row and the column that contains the number 2. So you imagine if this goes away and this goes away, you're going to get 4, 7, 6, and 9 left. Then next is going to be plus the entry 3. And then the determinant will be obtained by deleting the row and the entry that contains the entry 3 here. So that's going to be 4, 7, 5, 8 left. So now we are going to do the computation. 1 times this guy. So 5 times 9, that's going to be 45. Minus 8 times 6, that's going to be 48, right? 45 minus 48. Minus 2 times this guy. And then plus 3 times 4 times 8, 32. Minus 7 times 5, 35. And you can easily see that we are going to get -3 here, and then plus 12 here, and then minus 9 here. So at the end, you're going to get 0. In order to compute this 4 by 4 determinant, we are going to first expand along its first row. Now keep in mind, when we go along the first row, we are going to have the sign being alternatingly changing. Plus, minus, plus, minus. So this is going to be equal to. So the first one is plus, so I wouldn't bother about writing it. So I write the entry 2 times the determinant obtained by deleting the row and the column that contains it. So what you end up having is this smaller matrix here, right? So you copy it to the space here. Now we are going to move to the next one, 7. The sign in front of 7 will be negative. And then you will have to write down the determinant that is corresponding to 7 here. So in order to do so, we are going to cross out the row and the column that contains 7. What we end up having is 0, 0, 0, 2, 4, 0, 9, 8, and 6. So we copy them down here. Negative 1, the sign in front of negative 1 is plus. So we have plus. The entry is negative 1. And then here comes the 3 by 3 matrix by deleting the row and the column that contains the entry. Now we move to the next one, which is the last one as well. So the last entry is 16. We are going to have a negative sign in front of it. And then the determinant is going to be obtained by deleting the row and the column that contains 16. And so it's got to be 0, 0, 0, 3, 0, 0, negative 2, 4, 0. Alright, so now in order to compute this, I will have to compute each of 3 by 3 determinants here. So I will have to expand along that first row for each of them. And then when I do that, I will need to keep in mind the sign being alternatingly changing. Plus, minus, plus, plus, minus, plus, plus, minus, plus. Now, in order to avoid confusion, I'm going to divide them into 4 separate columns here. In each column, I will just compute the 3 by 3 determinant. I am not multiplying with the number in front of it, right? Just care for the value of the determinant here. So this is going to be, the first one is a plus for the number 3, and the plus in front is no problem, so I just ignore it. 3 times the determinant obtained by deleting the row and the column containing the number 3, so you can easily see what's left is 4, 0, 8, and 6. Next, we'll have to move to the second entry on the first row of this determinant. That is negative 2, and the sign in front of it is negative, right? So you are going to have a minus sign. The number is negative 2. And after deleting the row and the column containing negative 2, you end up having 0, 0, 8, and 6 left. Then you move to the next entry. 9, the sign in front of it is plus. And then you are going to delete the rows and the column that contain the number 9. So that's obviously leaving you with 0, 0, 4, and 0. All right. Then you compute this. So this is going to be 3 times 4 times 6 minus 0 times 8. Right? 4 times 6, 0 times 8. And then minus negative 2 times 0 times 6, 0 times 8. So that's obviously 0. And then plus 9. So you are going to plus 9 times 0 times 0, 0 times 4. So 0 times 0 minus 0 times 4. Obviously, this is going to be equal to 72. Let's repeat what we did for this one, right? Then you compute this. Of course, you're going to get a bunch of zeros here. So the first one is 0 because of this. The second one, 0 times 6, 0 times 8. So the determinant is going to be 0. So you're going to get 0 as well. And then the last one is going to be 0 times 0, 0 times 4. So you're going to add 9 times 0. So that's going to be plus 0. And so you're going to get 0. Similarly, you are going to get the same thing for the later ones. So in the end, you are going to get 2 times 72 minus 7 times 0 plus negative 1 times 0. and then minus 16 times 0. Right, so you're gonna get 144 as the final answer. So that's how we compute determinants using only the definition. And you see that it's very inconvenient. So in practice, that's very impractical because, for example, if you have to compute determinant of an n by n matrix, then you will have to first reduce it to n times determinants of size n minus 1 by n minus 1. For each n minus 1 by n minus 1 determinant, you have to compute n minus 1 times the determinant of size n minus 2 by n minus 2. For each n minus 2 times n minus 2 determinant, you have to compute n minus 2 times smaller size determinants. And then you keep reducing until you get to the 2 by 2 determinant. So this is like n factorial computations to do. And you know that the factorial is even much stronger than any exponential function. In practice, the fact is that the size n can easily get to over 100. And so it's impossible even for computer to do 100 factorial computations. That may take years or even errors to do so. All right. And so we have to find some other ways to compute determinant more effectively. And that's what is stated in the properties part here. First property, the determinant of the transpose of a matrix is equals to the determinant of the original matrix. Which means if you switch row into columns and columns into row, surprisingly, the determinant of the new matrix, AT, is the same as the determinant of A. All right. This is interesting because it implies that when you compute the determinants, whatever properties that you can do with the rows, you can also do the same thing with columns. For example, in the later properties, we have the property that says if we interchange two rows, the determinant will change sign once. That means if you interchange two columns of a determinant, then the determinant will change sign once. And whatever I stated for the row, you can do that for the column without any problem because of this property. All right, that's the first one. All right, the second property says that, well, we can compute determinant not only by expanding along the first row, we can expand along any row as we wish. However, we need to pay attention onto the signs because the sign is not going to be plus minus anymore. The sign is going to be maybe plus minus if you are on the odd row. But if you are on even row, that's going to be minus plus minus for odd rows. And then minus plus for even row. Again, you can do that with columns. You can expand along any column using the same idea here. That's just because of property number one. Whatever true for row is going to be applicable for columns as well. Now, in order to demonstrate what is going on with this one, right, I'm going to go back to our previous example here. So instead of expanding along the first row, I quickly realized that I have a bunch of zeros on the fourth row. So why don't we expand along the fourth row to utilize the zeros here? For the first row, it's going to be plus minus. That's because it's on the odd row. So the next one is going to be minus plus. If we expand along the third row, it's going to be plus minus. And if we expand along the last row, it's going to be minus, plus, minus, plus. All right, so that is going to be minus, plus, minus, plus 0 times the matrix that is obtained by deleting the row and the column here. So that's going to be this one, right? So because I know it's not going to contribute anything, so I'm going to just write dot, dot, dot. And then plus 0 times the determinant obtained by deleting the rows and the column that contain the entry here. So delete this column, this one, so you have 2, 0, 0, negative 1, negative 2, 4, 16, 9, and 8. You put them here, right? And then you subtract the next one is 0. The determinant is going to be determined by deleting the rows and the column that contain it. So that's going to be 2, 0, 0, 7, 3, 0, 16, 9, and 8. You can write them here. Now the last one is going to be 6. And the determinant is of importance, so we need to write them. So delete the row and the column that contains the number 6. You have this left. So 2, 0, 0, 7, 3, 0, negative 1, negative 2, 4. These are going to be 0, so I'm not going to care about them, right? So the last is going to be 6 times. Now, for this one, it's a 3 by 3 determinant. So you can expand along the first row, but that's not going to be a wise choice because expanding along the last row is going to be more efficient as you have more zeros here. So that is going to be, before we do that, we identify the sign for this guy. So if we go along the first row, that's going to be plus, minus, plus. The second one will be minus, plus, minus. The third one is going to be plus, minus, plus. So we have plus, minus, and plus. And then 0, 0, and 4. And then you will multiply with a smaller size determinant. For this one, if you delete the row and the column, right, you have 7, 3, negative 1, negative 2. But because I know that's not going to contribute anything, so I just write dot, dot, dot. The second one is 0, so deleting this and this. You get 2, 0, negative 1, negative 2, but because in front is 0, so I'm not going to care about them. The last one, deleting the row and the column that contains the number 4, you have 2, 0, 7, 3. 0, 0, so this is going to be 6 times 4 times, so 2 by 2 determinant, you can do 2 times 3, 0 times 7. So this is going to be 6 times 4 times 2 times 3 minus 0, and that's going to be 144. So you imagine that if we apply this property and we didn't write a bunch of unnecessary things here, of course, which we are not going to do, right? Then we can see that it saves us a lot of work compared to the previous computation that I made. Now the next 4 properties are going to be used very often. And I'm going to put a star for them. Right? These are what we really do in practice. The third property says that if A is an upper triangular matrix, then the determinant is solely determined by the entries on the main diagonal. Let's consider a concrete example to make it clear. This guy. It is an upper triangular matrix because all the entries below the main diagonals are 0. So only the entries from the main diagonal to above are meaningful here. And look what it is. It's in fact the upper triangle. That's why we call these types of matrices the upper triangular matrix, right? Now, for upper triangular matrix, we can expand along the last row or the first column. So say if we expand along the first column, then it's going to be 2 times the smaller determinant. Then we move to the next entry, that is 0. We don't have to worry about that. And the next, they are all 0. So only 2 times this determinant. But then when you move to computing the 3 by 3 determinant here, you are going to expand along the first column. You start with the number 3 and then multiply with the smaller determinant here. You wouldn't have to worry about the next steps because they are all zeros, right? So we are going to do 3 and then the smaller determinant. And then from here, we can just keep going until we get to the smallest determinant, and that's going to be 6. And so you are going to have 2 times 3 times 4 times 6 for granted, just by expanding along the first column of every determinant you encounter. And so you see that that's why you multiply along the main diagonal, and you're going to get the result. This is 144. And that's what the third property says. If a matrix is upper triangular, then just multiply the entry on the main diagonal. You're going to get the result. That's in fact just utilizing property number 2 above, right? 4. If B is obtained from A by interchanging 2 rows, then the determinant of B, the new matrix, after interchanging, is going to be the opposite of the original determinant. In other words, interchanging 2 rows, the cost is the negative sign. Now, if B is obtained from A by multiplying a row by a scalar, right? For example, the scalar is 2. That means B has a row that is 2 times the corresponding rows of A. The determinant of the new matrix with the row being doubled is going to be 2 times as much as the determinant of the original one. And in order to compensate for that, we divide the scalar that we multiplied. So if we multiply a row of A by 2, we get B. Then the determinant is 2 times A. So we have to divide 2. We multiply 1 over 2, divide 2 to make them balance. This is a way we use to compute a determinant of A. If B is obtained from A by adding a multiple of row to another, then although there would be a lot of entries being changed, surprisingly, the determinant won't change, right? So because of these nice properties here, especially the last one, we are going to use 4, 5, and 6 very often to reduce any matrix A to the upper triangular matrix. And you know that the upper triangular matrix is some sort of echelon form, right? So we can use row operations. 4, 5, and 6 are just row operations on matrices. Now we can do row operations on determinants to reduce the determinant to upper triangular or echelon forms. And then from there, we just multiply along the main diagonal and get the result done. However, when you do it with the determinant, be careful when you interchange 2 rows, the determinant will change the sign. And when you multiply a row with a number other than 0, then you have to divide the number to make it balance. Otherwise, you're going to get wrong answer. 7th property. This is the main reason for why people were in search for something called determinant, right? They are searching for a criteria to identify if a matrix is invertible or not, and a formula for the inverse matrix. The fact is that we do have that formula here, right? And the formula looks very elegant, but it is impractical. Why do I say it's impractical? Well, you have seen that computing determinant of A is not something pleasant. So even if you are going to delete one row and one column from A, the determinant of the smallest matrix is also annoying, right? Very troublesome to compute. And you have to compute this not only once. If A is an n by n matrix, then you have to do that for n times n, which is n squared times. For example, if you want to compute the inverse of a 5 by 5 matrix, then besides computing the determinant of the 5 by 5 matrix, which is time consuming, you will have to do 25 computations for the 4 by 4 matrices. Oh boy, I am not going to do that, right? And there's another thing that makes this formula is very annoying to use in practice. That is because if we are going to do that by hand, then we have to switch the row and the column at a certain time right here. So this means that the entry on the ith row and the jth column of the inverse matrix is going to be equal to -1 to the I plus j, which identify whether you are going to have a plus or minus, times the fraction in which the numerator is the determinant of a matrix, obtained from A by deleting the jth row and the ith column. So you have seen that we want to compute ith row, jth column entry, but then we have to delete the jth row and the ith column. So that is very unnatural here. Well, it's actually natural if you see the proof, but it's very unnatural in common sense. Why do we have to switch the row and the column here? And it's very easy to forget that at a certain time, the determinant of a product equals to the product of two determinants, right? We also oftenly use this one in practice, but not for now. All right, so now the example here. Use the row operations to compute the determinants of the following matrix. Of course, for A, there is no need to use row operations because it's just 2 by 2, so we multiply AD and subtract CB. Then use the formula for the inverse in the previous slide, the number 7, right? To compute the inverse if possible. So now the matrix A is A, B, C, D. And we want to find its inverse. In order to find the inverse, we need to double check if it has the inverse or not. And whether the matrix has an inverse, it depends on whether the determinant is 0 or not. So first, let's compute the determinant of A. A is a 2 by 2 matrix, so the determinant, you can write it this way as well. The determinant is going to be multiplying along the main diagonal and then subtract the product along the minor diagonal, so BC. Right, so now we see that if we multiply AD and subtract it by BC, we may get 0. And in that case, we don't have the inverse for A. If AD minus BC is not 0, then we can use formula to compute A inverse. All right, how are we going to use the formula? It's right here. So the formula says that when the determinant is not 0, then A inverse exists. And because this is a 2 by 2 matrix A, its inverse is going to be a 2 by 2 matrix. Right, so this is the first position on the first row, first column of A inverse. And then this is the second entry on the first row. And then we have this entry on row 2, column 1. And row 2, column 2 entry. Now, if you want to compute A inverse 1, 1, you are going to use this formula with I being 1 and J being 1. So A inverse 1, 1. So this is going to be equal to we are going to have the sign, and the sign is determined by negative 1 to the power I plus j, which is 1 plus 1. And then times the determinant of the matrix obtained from A by deleting row j, column I, right? So let's see what it is. Because we have identified I being 1, j being 1, so this is going to be deleting row j, which is row 1, and column I, which is column 1 of A. If you delete row 1 and column 1 of A, then you can see easily that only the D is left. And so that's the determinant of a 1 by 1 matrix whose entries is only D. And then divided by the determinant of A. But because we computed the determinant of A and we find AD minus BC, so we can put it here. And this is also the reason why that result has to be non-zero. If they are 0, you cannot divide 0, and you don't have the inverse. Now here, for the sign, you compute and you see that this is an even exponent, right? So it's going to generate the positive sign for you. So you don't have to worry about this. What is the determinant of a 1 by 1 matrix? The determinant of a 1 by 1 matrix is exactly that entry in the matrix. So you just write D without doing any computation. Now we are going to compute a inverse as the position 1, 2. So first we identify what is I and what is J. Now the sign is going to be determined by negative 1I plus J, but I is 1, J is 2, so that's 1 plus 2. And then you multiply with the determinant of something, right? Divided by the determinant of A, which is AD minus BC. What is that something? This guy, if you go back to the formula with the I being 1 and the J being 2, remember that. I being 1, J being 2, so you are going to have A 2, 1, which is the matrix obtained from A by deleting row 2, column 1. If you delete row 2, column 1, then what's left is only B, right? So the one that is left is B. And so here the sign is going to be negative because that's odd exponent. So you are going to have a negative sign in front. Determinant of the 1 by 1 matrix that contains only B, as the entry is going to be B, AD minus BC. All right, so now we can go ahead and fill into the blanks here. So A inverse 1, 1 is going to be D over AD minus BC. A inverse 1, 2 is going to be negative B over AD minus BC. All right, we have two positions left to compute. So A inverse 2, 1. Let's identify what is I and what is J. So negative 1, 2 plus 1. That's going to give you a negative sign because of odd exponent. The determinant obtained from A by deleting row 1, column 2, divided by AD minus BC. What is this guy? All right, again, one more time. If you want to compute IJ position, you got to delete row J, column I of the original matrix. This is the original matrix. J is 1 and I is 2 in this case. So row J, row 1. Column I, column 2. So you are going to get C as the only entry that is left. So this is going to be C. As I said, the sign is going to be negative. Determinant of C is going to be C. And you get the third entry. You fill it into the blanket. Now, the 2-2 position. A inverse on row 2, column 2. All right, of course, the I and the J's are the same. So 2 plus 2, the determinant of something divided by AD minus BC. Right, so you have I being 2, J being 2. So this is going to be capital A, J, I. But because they are all 2, so that means you are going to delete row 2, column 2 of the original matrix. Row 2 deleted, column 2 deleted. So what's left is actually only A. And so it's going to be A over AD minus BC. And there we go. When the determinant is not 0, we have this as the formula for the inverse of the 2 by 2 matrix. Let's rewrite this one as 1 over AD minus BC times the matrix, that is D, A, negative C, negative B. Now let's consider the second one, right? B. Now the determinant of B, previously we have seen how we compute the determinant of B by expanding along the first row. In this case, I would like to use row reduction to compute the determinant here. And we are going to mainly use 4, 5, and 6 to turn the matrix given into the upper triangular. So what I'm going to do is I'm going to make changes on row 2, make it become row 2 minus 4 row 1, and make changes on row 3 become row 3 minus 7 row 1. If you multiply one row by some number and then add to the other row, of course, you are going to change all the entries on these rows, and so you are going to get a new matrix. But if you do this, the new matrix will have the determinant being the same as the determinant of the original matrix. So 1, 2, 3 are staying unchanged. Row 2 minus 4 row 1, so 0, negative 3, negative 6. Row 3 minus 7 row 1, 0, negative 6, negative 12. In order to make 0 here, you subtract row 3 by 2 times row 2. You are going to get a new matrix, and its determinant will be the same as the original one, and this is because of property number 6. So first row being kept, second row being kept, the third row will be changed, 0, 0. Well, we actually obtained the triangular matrix. All entries below the main diagonals are zeros. When we get to the upper triangular matrix, then computing the determinant is simply just multiplying the entries on the main diagonal. And these are going to be 1, negative 3, and 0. Of course, you instantly get 0. Here, that's property number 3. Right here, I use property number 6. And right here, I use property number 6. The determinant of B has been found to be 0. And so by property number 7, B is not invertible. Here, because you will mostly deal with 2 by 2 and 3 by 3 matrices. And so I'm going to show you some other ways to compute the determinant of 3 by 3 matrices that, in my opinion, is quicker and easier to use. Remember, this is only true for 3 by 3 matrices. In order to compute the determinant of 3 by 3 matrix, on a separate piece of paper, we are going to copy the whole matrix again. Then copy the first 2 columns one more time. Then you start multiplying across the main diagonal. So doing this, you are multiplying 1, 5, and 9. So what you are going to get is 45. So you write 45. Next, you are going to add with. You do along the second one here, right? So that is going to be multiplying 2, 6, and 7. That is 84. And then you add next one. 3 times 4 times 8. So that's 96. Now, there is no way you can go further, right? So let's stop here. Now then you will start going from below to above. And when you do that, you use subtraction. So you will subtract this guy. And then you are going to subtract this guy. And then you are going to subtract this guy as well. So there will be 3 subtractions. The first one means you multiply 7, 5, and 3. You are going to get 105. The second one means you multiply 8, 6, and 1. You are going to get 48. The third one means you multiply 9, 4, and 2. That's obviously 72. And all of these will be subtracted off the result that you had before. Right. So for the first 3 main diagonals, adding. For the later 3 minor diagonals, subtracting. So you are going to get 0. Well, there actually is another method to compute 3 by 3 determinants. That is a little bit quicker because it does not require you to rewrite a bunch of things here. However, it's going to be a little bit messy, right? And you need to have a little bit strong mind to control. Let me show you the other way. I'm going to use the blue ink for what we are going to add and use the red one for what we are going to subtract. So first we are going to add this one. That's the main diagonal. So that is going to be 45. And then the triangle that are kind of parallel to the main diagonal. So this means you multiply 2, 6, and 7. That's 84. And then you multiply 4 and 8 and 3. So that is going to give you 96. Now it's time to subtract. 7, 5, and 3. So subtract 105. And the triangles that are parallel to the red line here, 4 with 2 and 9. So that is going to be 72. And then 8 with 6 and 1. All right, so that is going to be 48. And you get exactly the same thing as above. So this is going to be 0. All right, and you can see that there really is a mess here. So stay strong, otherwise avoid this. Whatever, I give you all possible ways to compute 3 by 3 determinant. You can either expand along the first row or any column, right? You can also use row reduction. You can also use the method here, or you can also use the mesh here. All right, which one works best for you? Use that. I would like to give you a short proof for number 5. This is easy, what you can understand, and it is not utilizing something that you haven't learned, right? So number 5 says that if you scale up a row of a matrix A, you get a new matrix B, and the determinant of that new matrix is R times the determinant of A. In other words, the determinant of the original is 1 over R, the determinant of the new one. And the 1 over R is actually just to queue up the scale that you gave to get B. All right. So you are going to obtain B by multiplying row I by R times row I. And so what actually B is A11, A12, because you do not do anything on row 1. All the rows are going to be kept the same, like the last row, AN1, AN2, ANN. Only the row I will be looking a little bit different. That is, you are going to give every entry a scale by a number R. So R times AI1, R times AI2, and then R times AIN. Now let's compute the determinant of B. So use property number 2 and expand along row I to compute the determinant of B. And the determinant of B is going to be, all right, so what is that formula when we expand along row I? So the sign can be positive or negative depending on whether I is odd or even, right? And that is going to be negative 1, 1 plus I, times the first entry on row I of B, that is R times AI1. And then multiply with the determinant of B I1. Right, this is the matrix obtained from B by deleting row I, column 1, the row and the column that contains the entries that you took out. The row and the column that contains the entries that you took out. Then you move to the next entry, right? So the sign will be determined by negative 1 to the 2 plus I. The entry is going to be R times AI2, and then the determinant of the matrix obtained from B by deleting the row and the column containing AI2. All right, and then of course plus dot 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 plus. The last one is going to be N plus I, and the entry is going to be obviously R times AIN, and times the determinant, multiply the determinant of the matrix obtained from B by deleting the row and the column that contains the entries that you took out. So that is going to be row I, column N, IN. Now, let's take a look here. We have R, R, and R. So we can literally take it out as the common factor. So you take out R, what's left inside is negative 1 to the 1 plus I times AI1 times the determinant of BI1. But I'm going to replace BI1 by something. And that something is from the observation. If you delete row I of B and the column 1 of B, then what's left is going to be this and this. Isn't it the same as the one after you delete row I and column 1 of A? You're going to get something here and something here, being the same as B, because the only difference between A and B are on the ith row, and you have already deleted the ith row, so there is no difference between what's left here and what's left here, right? So I'm going to replace this by AI1. And similarly, after you took out R, you have AI2 and the determinant of BI2, but then BI2 is going to be the same as AI2 because you deleted the row I, which is where you have the differences between the two matrices. So there is no difference anymore after deleting. And then negative 1 to the N plus I times AIN times the determinant of BIN, but BIN is the same as AIN. All right, so now look, what you have here is exactly the right-hand side right here. If you compare them, they are exactly the same. And so what you have over there below is going to be exactly the determinant of A. So this is going to be exactly the determinant of A, and this is equals to R times that. The matrix C is a 3 by 3 matrix. First of all, you have to compute the determinant of C. We utilize property number 5, with the R being 1/2. Alright, so row 1 becomes 1/2 row 1. If you multiply row 1 by 1/2, you're going to get 1, 1/2, 3/2. Now, if you multiply one row by a scalar, you get a new matrix. Of course, this is different from this. But the determinant of the new matrix is R times more than the determinant of the original matrix. In other words, the original matrix is going to be 1 over R times the determinant of the new matrix. But the R in this case is 1/2. And so you actually kind of have this being 2 times the new determinant. And that's the difference between performing the row operations on matrices to get row reduced echelon form and performing row reductions on determinants to obtain the upper triangular form. All right, next we are going to use property number 6 here. We make changes on row 2 and row 3. Row 2 will become row 2 minus 3 row 1. And row 3 will become row 3 minus 7 row 1. Don't forget the number 2 in front. We are going to apply property number 6 one more time. And we are going to make changes on row 3. In order to zero out this one, we use row 2 to zero out. And we are going to subtract row 3 by 3 times row 2. Row 1 and row 2, they have no change. Row 3 minus 3 row 2, so that's going to be 2. Now, it's in fact the upper triangular matrix. And so we can go ahead and say, well, we are going to use property number 3. We rewrite the number 2 that we already had. The determinant would become the product of the entries on the main diagonal. And so the answer is going to be 2. Now the determinant of C is 2, which is not 0. That implies that C is invertible. In other words, the inverse of C exists. Right, so now we want to compute C inverse. Remember, C inverse is a 3 by 3 matrix because C is a 3 by 3 matrix. So we have 9 entries to find. C inverse on row 1, column 1. So I is 1, J is 1. So the formula says that you will have the sign determined by -1 to the exponent I plus J. So -1, 1 plus 1. All right, and then that is multiplied with a fraction whose denominator is the determinant of the original matrix, which is determinant of C. And because we have computed the determinant of C, we can go ahead and replace the denominator by 2. That's the result that we found for determinant of C. On the top is another determinant. Instead of writing DET, I'm going to use the pair of vertical straight line. This is the determinant obtained from C by deleting row 1, column 1 of C. Delete row 1, delete column 1. All right. You can see that if you do so, you're going to get 2152. All right. So instead of writing C11, we are going to get 2152. So what you actually have for the first position is -1/2. And so I'm going to go ahead and fill in the blank. We are computing the entry on the first row, second column of C inverse. All right. According to the formula above, right here, this is going to be negative 1, I is 1, j is 2, so 1 plus 2 times the determinant of something here divided by 2, the determinant of the matrix. This guy is the result. If you write it down, it's going to be C21. And the notation here means that you are going to delete row 2, column 1, right? So you can see there is a switch here. Row 1, column 2, but we are going to delete row 2, column 1 on the original matrix. If we delete row 2, column 1, this is what we end up having, 1, 3, and 5, 2. So we're gonna get 1, 3, 5, 2. Computations is going to give you 13 over 2. So we go ahead and write 13 over 2 right here. Now let's compute C inverse on first row, third column. According to the formula, it's going to be negative 1, 1 plus 3 times the determinant of something here divided by 2. This guy is going to be obtained from C not by deleting row 1, column 3, but by deleting row 3, column 1. So it's kind of a little bit awkward, right? Row 3, column 1. So you have 1, 3, and 2, 1 left. So we are going to have 1, 3, and 2, 1. So you end up having negative 5 over 2. So we have negative 5 over 2 right here. Now let's compute the second row. The entry on the inverse matrix at the position row 2, column 1. So negative 1, 2 plus 1 times the determinant obtained by deleting row 1, column 2 of the original matrix. So row 1, column 2. Right, you can easily see that that's going to leave you 3, 1, and 7, 2. So you get positive 1/2. So this is going to be 1/2. Next, we compute the entries of the inverse matrix at the position row 2, column 2. So negative 1, 2 plus 2 times some determinant divided by 2. And again, 2 is the determinant of the original matrix C, right? That's always in the denominator. This guy, you look at C and you delete row 2, column 2. If you delete row 2, column 2, well, what you end up having is clear, 2, 3, and 7, 2. This should give you negative 17 over 2. C2, 3, the entries on row 2, column 3 would be equal to negative 1, 2 plus 3, and then times the ratios of some determinant divided by 2. This guy is obtained from C by deleting row 3, column 2. Row 3 deleted, column 2. Alright, so what's left is going to be 2, 3, and 3, 1. And the computation is going to give you 7 over 2. So you can fill in the blanks that you have here. So we need to compute C inverse row 3, column 1. And so the answer is going to be 1/2. And then you move to row 3, column 2. And so you're going to get negative 3 over 2. The last entry, computation is going to give you 1/2. Now you can go ahead and fill in the blank in the row here. Right. 1/2, negative 3/2, and 1/2. And that's how we compute the inverse matrix using property number 7. The matrix that I'm considering is the 4 by 4. So the determinant of D, we are going to switch row 1 and row 2. Interchange row 1 and row 2. So row 2 becomes row 1 and row 1 becomes row 2. The other rows will be kept the same. Why do I need to leave a blank here? When you compute a determinant, if you switch two rows, what you need to do is adding the negative sign. That is because we are using property number 4. We are interchanging the rows. All right. Don't forget about this negative sign. Now that we have the number 1 on the top, we are going to zero out all entries below it. In order to do so, we are going to use property number 6. So row 2, if you want to zero out the number 2, you subtract it by 2 times row 1. Row 3, if you want to zero out the number 3, you subtract it by 3 times row 1. And row 4, if you want to zero out the number 1, you subtract row 4 by row 1. So I'm going to use property number 4 again. And I'm going to switch row 3 and row 4. For property number 4, whenever you switch two rows, the sign is going to change one more time. So there's another negative sign that has to come out. Now next, we are going to use this negative 1 to zero out the negative 5s here. Alright, next, I'm going to zero out negative 5 and negative 5. So in order to do so, we are going to apply property number 6 one more time. Right? We are going to use row 2 to zero out row 3 and row 4 here. Now, because the negative sign and the negative sign will cancel out each other, so what a relief, right? We don't have to worry about them anymore. Now we can focus on the computation. Seems like I made a mistake when I copy something here. There should be a negative sign, right? So negative 3, and then 0. If you subtract 5 times, you're gonna get 0 here. You're gonna get negative 1 here, and you're gonna get 9 here. Similarly, you subtract 5 times row 2, so you're gonna get 0 here, negative 3 and 8 here. All right, so in order to do so, we apply property number 6 one more time. This time, we are going to make changes on row 4. Row 4 becomes row 4 minus 3 times row 3. And so this is an upper triangular matrix. The determinant is going to be equal to the product of the entries on the main diagonal. So that's going to be 1 times negative 1 times negative 1 times negative 19. And you're going to get equal to negative 19. Right. Anyway, this negative 19 is not 0. The determinant of D is not 0. So D inverse exists. D is invertible. And we can find the inverse. All right. Now let's compute D inverse. 16 entries. All right. Let's compute D inverse 1, 1. So that is going to be negative 1 to the I plus j times, all right, some determinant divided by the determinant of D. But the determinant of D is negative 19, so I can go ahead and replace it by negative 19 here. What is the determinant on the top here? It is denoted as D11. This means you are going to delete row 1, column 1 of D. Right. So if you look at D and delete row 1, column 1, what are we going to get? delete row 1 and column 1, what we actually will have is 3, 2, 4, 4, 5, 6, and 2, 2, 1. So we write it here. To compute this guy, you can use expansion along any other row or any other column. You can do row reduction, but for 3 by 3, the quickest way is to use one of the methods I showed you in the previous class meeting. If you do so, you are going to get the following result. 13 over 19. Let's do one more. The inverse at the position on row 1, column 2. That's going to be negative 1, 1 plus 2, because I is 1, j is 2. And then you are going to multiply with some 3 by 3 determinant divided by the determinant of d, which is negative 19. This is going to be d, and you will have to switch the row and the column here. All right. So instead of 1, 2, that's going to be 2, 1, which means you will have to delete row 2, column 1. Row 2, column 1. Row 2, column 1. Well, you end up having 1, 1, 1, 4, 5, 6, and 2, 2, 1. Right? You compute the 3 by 3 determinant, and don't forget the sign in front is going to give you this. So I'm going to finish this one by giving you the answer, and I encourage you not to compute all 16 entries here, but at home you try to compute several more entries to have the feeling of what is going on, right? And that's also a good practice for you. Don't compute all, just compute 2 or 3 more entries on your own. If you do everything correctly, the answer should be here.